Welcome everyone. We'll now hear from Sanjay for the second part of the tutorial.
Thank you. So we'll continue from, this is a little loud, isn't it? It's echoing. Can somebody turn the volume down, please? Thank you. Yeah, so I'm going to switch modes. Yesterday was sort of a more tutorial style, and today is sort of more a research talk style. What I'm going to be talking about is sort of led by PhD student Litu Raut at UT and my colleague Konstantin Karamanis. And in close collaboration with sort of Google Research and DeepMind. So Yujua and Vincent Chu are in the Pixel team, and they were instrumental in getting the things which we are talking about productionized in the Pixel platform. And Abhishek was then in the Google DeepMind. Nathaniel is in the Imagine team. Now he's actually, I think, in the VO team. But so he was with him. We collaborated to get this productionized within Imagine. So that's the sort of context for this work. So let me get going. So yesterday we talked about sort of training-based and training-free approaches. So these are sort of algorithms for training-free image inversion editing. So I know that we talked about some of these things yesterday, but I thought I'll quickly recap. The problem setting is the following. I've got some ground truth image. I've got an imaging system. There's a linear, there's some maybe linear or nonlinear operator. There's additive noise. And you've got measurements Y, which is some function of the imaging system plus noise. And the problem is, given this, you want to reconstruct that. This is I'm just summarizing what we discussed yesterday. And as we saw, this problem is ill-posed. And because there are many, given this, there are potentially many possible solutions. And so you want to use if you knew the distribution of how images look like, you'd use that prior to regularize. And that we made this more concrete yesterday when we talked about the connection between inverse problems and posterior sampling. So again, this is all stuff we talked about yesterday. I'm just quickly recapping that. And so here are several examples of what kinds of inverse problems you care about. One is so-called free-form in-painting. Parts of it is deleted, and you want to reconstruct what is there. Or motion deblur. So there's A is a motion operator, and so you want to go from this back to this. Another is sort of the classic super resolution problem. You have a low resolution pixelated image. You want to get a sharp image out of it. Or a Gaussian blur, so which is a different blurring operator. It could be linear or nonlinear Gaussian blur, and you want to get the image back. So these are examples of sort of what people think of as classic inverse problems. But there's a different community which has been thinking about these types of problems. They have merged together. There's the these are the image editing community, which also are essentially a form of posterior sampling, as we talked about, as we saw yesterday. This would be these kinds of problems. I give you a prompt. This is my conditioning, and you want to generate an image consistent with the prompt. Or you want to give a stylization, which is I give you a style, I give you text, and I want to generate something consistent with these two here. Okay, these are called stylization. And the other problem is content style composition. So I'll give you some content, I'll give you style. These are all just one shot, one image. And during test time, you want to generate an output which is consistent with this content and this style. And so diffusion models are sort of most recently sort of flow models, which are very closely related to diffusion models, are sort of the very good generative priors using which you sample these kinds of things. And we talked about this pipeline yesterday about different types of algorithms, and we'll build on that today. So in terms of scale of these models, this is sort of a recent local history. There are two types of models. You can talk about pixel space or latent space. I didn't even bring in the latent thing yesterday. I talked straight in pixel, but I'll bring in what latent is in a second. Okay? In a pixel space model, if you're dealing with a 1024 by 1024 image, it's a 3 million dimensional vector. But most current models actually operate in latent space, meaning you train a VQVAE, a various autoencoder, to project down to order of 10,000 dimensions. That's roughly the latent space dimension. All your algorithms are actually operating in the latent space or in some cases, such as stable cascade, in multiple latent space. There's a fast latent, and there are multiple levels of latents. Yeah. But you want to work in latent space because it's a much lower dimension and computations are faster. Of course, there are interesting issues that come up because you're working in latent space, meaning if you're solving inverse problems, the measurements are usually in pixel space, but your diffusion is happening in latent space. So how do you resolve that? Some interesting questions. But in terms of scale of this model, stable diffusion, which was about a 1 billion parameter, really, diffusions were there since 2015 in the Sol Dickinson et al. Paper since then. But it became sort of widely popular after the release of stable diffusions, an open model where people could start playing with it as a community. And Stability AI has a series of models. The current state of the art is SD 3.5, which is no longer a diffusion model, but actually a flow model. I'll talk about what a rectified flow model is in about 15 or 20, in about half an hour from now. The sort of today, the most powerful open generative model is Flux, which is again a flow model. It's a 12 billion parameter model. These numbers will become important when you see what you can do in an algorithm. If you want to sort of do gradient updates in these kinds of scales, and you want to do it within seconds, you will realize that that really constrains you on what kinds of algorithms can be deployed. And that's what our story is going to be through this presentation. Okay, so this talk is about a series of 4 papers with very little emphasis on the first 2 and more on the second 2. So essentially, we started working on this sort of in 2022, and we developed PSLD, posterior sampling with latent diffusion, which was the first algorithm to actually solve these kinds of inverse problems in latent space of diffusion models. So it essentially, we talked about DPS yesterday. How do you sort of do DPS in latent space is essentially what PSLD is. And then STSL, we realized so this still suffered from the same problem we talked about yesterday, which is it's a first order approximation. So STSL was a second order approximation algorithm where we sort of looked at the second term of the expansion. I mean, I'm just building since we have yesterday's talk as context, I can sort of talk a little bit more in detail here. But dealing with Hessians is very, very expensive at 12,000 dimensions. So this does it basically does random projections and essentially treats a local stochastic approximation inner loop to give correction to the guidance. So that was STSL. And this paper the first one was within UT. The second, including Alex DeMarquis, who was at UT, and now he's at Berkeley. Yes.
So when you do PSLD in the latent space, you compute the expected final point in the latent space and just pass it through the
Yes, but how do you get consistency is tricky if you just push it back. So maybe I'll talk a little bit. Can I punt your question for 5 minutes till I actually get to PSLD? I'll come to that. It's a good question. I'll talk about what we do in PSLD when we get there. STSL is sort of inverse problems and editing using second order methods. And this was the first in the line with the pixel team. And then what I'll talk about is sort of doing things at scale with RB modulation, RF inversion. The issue essentially is computing back propagation is very expensive. So how do you get around that? These two really had to do, they involve you have to backprop to this core network. And so it's slow. And I'll show you what I mean by slow in terms of times. These are much, much faster algorithms. And these are the ones that have been productionized across various platforms. These are not fast enough to be actually in production. Okay, so background, again, I know you've seen this like multiple times, but just because there's a talk, let's just very quickly go through this. What's a diffusion model? Well, you start from an image, you noise it using a standard OU process to get pure noise. We know the reversal, yesterday we talked about it, Anderson's reversal, discretization, and so what you have is a score, and you start from pure noise. This is just the vanilla diffusion model, and you'll get an image in finite number of time steps. Essentially, as we sort of saw yesterday, it's a Markov process-based sampler. This is an unconditional sampler. One nuance that I'm not going to really talk about, yesterday I just talked about it as just sampling images. really the base models that are trained are not just pure images, they're text guided. So it's jointly trained on image text pairs. So it comes for free, text guidance comes for free. So what you want to do at test time is everything else. You have already this thing for free in your system, okay? This is something to keep in mind when we talk about this. Okay, all right. And as I said, the posterior sampling problems is sort of conditional sampling. This is an example. This is my measurement y, and I want to sample an x consistent with this. This is the other example. Okay. All right. Again, this is a recap from where we were yesterday. Recall the standard. If I were to have a training-based approach, I would have a conditional score that I would need to use to drive the diffusion. We can do the Bayes rule. Exactly, we did this yesterday and saw that we can decompose this conditional score as the sum of two quantities. One which is unconditional score, unconditional annealed score, importantly, which is known. Which from now I'll call it S theta xt of t, because this is parameterized by some parameters theta. The input is xt and time. There are two inputs. One is sort of quote unquote the current noisy image, and the other is time. And this part is unknown, and we need to figure out how to approximate it on the fly. Now, I'm calling this the noisy image. Reality is that's not true. What you actually have are two spaces, the x space of pixels and the z space of latents. So you have, the pipeline is actually that you take your image, you encode it to your latent space, your diffusion is in latent space, so the score net is this. So what stable diffusion on any of these things will come is three things: an encoder and decoder, along with a score in that latent space. So we are always operating within a latent space. So really this input should be ZT. I'm going to fudge between X and Z in this talk.
And you have a dog. So it's not necessarily that you want an image of a dog conditioned on a flower, right? You want to mix them two in some way. So are there other ways of thinking of how to merge the two?
There are, so this, I am asking, yes. Sorry. Let me, okay. I am in this problem imposing that I want the style of this and the content of this. So what does those words mean? Style basically means somebody has built a style network already. It's a differentiable box which will say, if I put two images inside it, it's going to give me a score on alignment style. And that is going to be my loss function. So when I'm using these English words, really there's a neural network which knows what these words mean and give you numerical scores. Okay. So in this problem, I want style from this and content from that has a specific meaning. Okay. All right. So this is sort of the posterior sampling setup, and the question is, how do you approximate this during test time? This is where we were. Now I've sort of brought this thing where we ended yesterday, essentially. Okay, so let me first talk about PSLD. I just have one slide, so I'll talk more about it since you have asked a more detailed question. So PSLD was the first algorithm to solve these inverse problems for in latent space, and it generalized the DPS algorithm, which was in pixel space. So roughly, what you do is the following. Okay, you take let's recap what DPS did. You had a noisy pixel space image, project it forward, and then perform the loss with that treating that as an image and backprop it through. Here, my measurements, let's say let's talk about an infilling problem. Your measurements are actually in pixel space. So you take that and send it through the decoder. Okay. So you will get some particular part of the image. Okay. You could just apply the loss on it and push it back, but that's not what we do. What we use is the following principle. If your solution was correct, okay, and you go to the encoder and decoder, you should get back the same image. We could have done exactly DPS as straight DPS by just pushing it up and coming back down. The problem is the VAEs are not good when they're out of distribution, the images. So that losses are not very good to backpropagate, and people tried that and it wasn't working very well. So instead, what we did is the following. We pushed it up to the pixel space. Then you merge these two images together. You have measurements. You predict something noisy. You can, for an infilling, it's very clear how the merging is, right? You just paste them together and then decode. That is your signal, and that's what we deal with. You now build a loss function on it. Mathematically, you decode the image. You first take your latent, you have a latent, you push forward in latent space. So this is the 2D, Z bar T. You decode it, you merge it with whatever measurements you have, re-encode it, and if things were indeed correct, this loss would be 0. It would be a fixed point. And you can prove sort of baby linear theory, saying that if everything is linear, this is the correct thing, it will converge and all that stuff. But in practice, now you see, this is the idea of PSLV. And so this is so what you do is then you backprop that error. This is my guidance term for my score in the latent space and push it forward. Now, that's roughly the algorithm, but let's think about what the problem could be. Look at this Z bar T, okay? This Z bar T is some 2D-based estimate, which is affine in the score. So you are trying to backprop the gradient you're taking with respect to ZT. That means you need to backprop through the score, to the input of the score network every single time. And as the score network scale from billions, in the billion size to 12 billion size, this is already very, very expensive. And what do I mean by expensive? I'll show you in terms of concrete times in a second. Yes. In test time, you're doing backprop in the following sense. Let's use a vanilla diffusion model, okay? No measurements. You tell it to generate a dog. Let's say it's text condition, generate a dog. You run it, you're going to get some image of a dog. Now I want a dog in golden style, say, okay? So you have a loss function, or I give you half a picture of a dog. Well, because we are talking the infilling context. I give you half a picture of a dog. I need to make the dog consistent with this. So what do? I take whatever image I've generated, push it forward in latent space to the initial. This would be what a dog would have looked like in latent space.
By initial, you mean the half dog picture that
No half dog. There is no half dog. I running the generative model. It's trying to generate some sort of a dog. There's no half dog business right now. It's actually generating a whole dog. Okay, and the latent of a dog is there. Now this latent of a dog should be decoded to get a dog in pixel space. This has nothing to do potentially with the dog I have in mind, with the half dog. So what do? So this is right now, I take the half dog, which I have, that's Y. The operator says which half I know. This says the other half, paste it together. And then this is an image which is weird. It's encoded back, and look at my dog, which I originally had. Look at the error between that. The gradient of that tells me how off I am. And that gradient needs to be backpropagated to the input, the noisy latent, to turn the noisy latent towards the correct dog. So this test time optimization requires gradient computations in test time.
So gradient of the encoder and decoder.
Yes, this is gradient with respect to ZT. Normally when people say backprop, they're talking with respect to theta. I'm just using the same word to say there's a gradient. The gradient is being backpropagated. This is not a neural network training backpropagation, but there's a gradient taken with respect to the input. In that sense, it's a backprop.
That's just like approximated by small point nearby and then difference.
No, that is a prox. This is actually, so technically I need to take a gradient with respect to ZT. That means to do that, I need to send it back through the score network. Okay, we can discuss this. Yeah. Z bar T is the following. I have my noisy latent image. I now want to figure out what the clean latent image would look like. And that's just a conditional expectation overall on the image manifold, condition that my noisy image is right here. So that Z bar T is a conditional expectation over all possible clean images that are consistent with my noisy latent. Okay, and that is because of Tweedy's formula affine in the score.
And how do you compute this? Just by taking a lot of...
This is single sample.
Oh, just one sample.
This is one, I've just given you one half dog. I need, at each step in my diffusion, I need to do one such calculation. Okay, this gradient is with respect to the input to this core network, which means in latent space, it's a 12,000 dimension vector. So it's not the model size that's important for this. This is the latent dimension. That's the dimension with respect to you're taking gradients. Okay.
Sir, so basically the input that we want, the text from that information is coming through Y.
The text is not in this figure at all. So this S theta actually has comma Z. Y is the half dog. So I'm just talking about a clean image problem right now. Text, I'm not even talking about text guided. There's always guidance of text. This core network actually has 3 inputs. There's a Z, that's a noisy image. It has time, comma, text encoding, which will tell, and it has, so it'll, the text encoding is fixed to say dog, so that you're generating dogs by default. Now I'm trying to twist it to be consistent with that dog, which is for which I have a half dog an image. Okay.
So the main issue is that you don't want to differentiate through that decoder and
that is all.
encoder.
That is explained, and I'll tell you what it means in terms of actual time in just a few minutes. Okay. So this is PSLD. This was, and in the interest of time, I was planning to spend 1 minute on this slide. I will skip over some of the PSLD results so that I can move forward to sort of what I want to get to. The problem with PSLD had the same bias of DPS. It's a first order approximation because finally just a 2D correction. So you can do a second order expansion. There's a trace of a Hessian because it's a projection and all that kind of stuff. I don't want to even talk about this algorithm today, except to say it did a correction to the PSLD in the same latent type of pipeline. Okay. This is again expensive for exactly the same reason. You need to backprop to the input. Okay. But you may ask a side question. What is the advantage of doing the second order correction in terms of practice? Okay. I think this figure is quite interesting to see. Are you able to see details in the back of this eye? Otherwise, I'll zoom things up. Can you see this? So this is the ground truth distribution. You can see the eye slit. If you look carefully, you can actually see an eye slit there. Okay. This is the input corrupted. Because it was corrupted, it has vanished. PSLD and other algorithms, it looks, the dog has, this blurry dog has been deblurred. It looks better. But if you look at fine details, it's gone. What second order correction does is recover fine details. That's real, and this makes sense because what does a 2D projection really do? It's a conditional expectation. Given I'm at some point in the diffusion, I project forward to this image manifold, and I'm averaging over all images with the constraint that when they move forward, they'll lead to this particular point. But that means an average of images is no longer a good image. It gives blurriness, especially if it's a linear space, of course, it's a valid image. But if the manifold was curved, then you're off that. You're going to get blurred. And this is sort of, that intuition is what you see here. Okay, that second order correction is actually important if you want this deblurring. You could ask how much does it cost and all that stuff, and that's a separate talk. So this is the backstory for what I want to talk about today, which is RB modulation and RF inversion. The problem with those STSL works well, but it is very, very expensive because of this gradient. Okay? So we came up with 2 algorithms, RB modulation for content cell composition, which actually, and then a new algorithm, which is gradient free, which I'll talk about for the last 20 minutes, which is good for certain types of applications. Okay. So the RB modulation, the key thing is that it avoids backpropagation to this core network. And I'll talk about what I mean by that. In terms of time, let's look at some numbers. I talked about training-based approaches. You could fine-tune the theta itself, right? I can take a small batch of images and fine-tune theta, the usual backpropagation. In test time itself, I could do fine-tuning, test time fine-tuning of the network for a particular task. Or maybe if I knew the type of style I wanted, I could pre-compute with a small batch. Typically, per style and content, you need order of tens of samples to actually fine tune it. Okay, if you just use 1 or 2 samples, it collapses because you're putting too much weight on a few things. The network breaks. So you need order of tens of samples, and here the gradients are computed with respect to the weights of the base model. It takes about LoRa type fine tuning takes about 20 minutes per style. Full fine tuning is hours. This is on A100. I'm talking about all this is about one A100 type GPU numbers. Okay. Let's now talk about test time optimization. If you're doing test time, these kinds of algorithms, PSLD or STSL, one sample is enough because you're not changing the network in any way. You're sort of taking backprop with respect to the input. And PSLD for a 1 billion size models took about 10 minutes. A different group came up with an algorithm which built on PSLD called P12, which takes about 20 minutes. It gets better quality. STSL is also order of this speed. It's order of tens of minutes. RB modulation does something else. If we can do it in 40 seconds per image for sort of stable cascade is a 4 billion size thing. So therefore, this actually could be productionized. And so that's what I want to talk about as the first thing. And then I'll talk about something which is even faster. So RB modulation essentially does the following. Let me just go back to this. Remember what we had. We had the diffusion had after the base, there's the base model, and there's some other term we are trying to learn. Instead of saying that I'm trying to learn this, I'll put any function I want and try to formalize the following optimal control problem. Find a function u of x, okay, such that it minimizes energy in some form, and a terminal constraint which basically says that whatever you end up with should be consistent with your measurements. Okay, we need to do all the latent stuff. Let me just ignore the talking through the latent. You can talk about just reformulating this as an optimal control problem and say, what is that controller you would need if you want to do this? And it turns out one way to think about this from an optimization perspective is the following. What we did previously with PSLD is forget the latent part. Let's just talk about DPS. We projected using conditional expectation to the manifold of images, and then compared that with the measurement and backprop that. Instead, you can do the following procs. You push forward to the manifold of images. So you've got a conditional expectation. Then do a local search, okay, in that space. Look for some other image nearby which is consistent with images, and then noise it back to 2xt minus 1. Okay, so that's essentially what happens with RB modulation. This leads to that kind of an algorithm. Okay. There's another piece as well, which ties in with the question you asked: how do you disentangle content and style? This is now sort of transformer engineering. Essentially, the parts of the attention which focus on content are different from the style. So you can sort of edit them separately without entangling these things, okay, roughly. So what you have to do is to do so when you're given an image, you personalize the score for that image and use that. That's the content personalization, and the style is going through this. This one?
Is optimization happening at test time?
Yes. So we are not solving this optimization problem. What we do is we do a one-step gradient. What I described is sort of a one gradient step towards this solution, and then move forward anyway. Don't ever solve this optimization. That's why I said it's equivalent to this kind of a prox algorithm. What you do? Replace this by U of t. This is not what we do, but this is the mental. If you could spare computation, replace this by U of t, and say find a U of t starting from where I am. So it will not be 0 then, it will be at whatever place I am. Some energy function, squared loss. I want to find a good U of t, and a terminal constraint that says wherever I end up, it should be consistent with y, the measurements. This is my optimal control problem, and this will be the optimally controlled SD.
G is some function that will tell whether it actually has that feature or
not. It's a style network. So G, for example, in style would be a style. Oh yeah, people have differentiable style networks. So G would be that, it's a scorer. It's basically any reward function, okay? More generally, if you have a differentiable reward function, this is what you would do. So you can generalize this for other reward type of things. You're trying to find, that's all, yeah. Yeah, so what this leads to is the following algorithm. You take, you do the standard projection down. So you got a mean image. Then in a neighborhood of it, you do a gradient in the space of images with respect to the measurements. So you got at some other point there. And then forward prop it, forward noise it to get back. You start at time t, you noise it to time t minus 1. That is your new latent. Okay, that's essentially what this pipeline would lead to. That's right, that's the iterative loop, okay? And so these some examples of what happens with this kind of an algorithm. So I've shown you this image already. So in the interest of time, actually I have time, okay. Yeah, we can do all these kinds of compositions. Maybe because I have time, I can go through this. I said there are two things going on. One is this optimal control, and the other is a transformer engineering thing. One may ask, do you need both? What happens? Can you just do it sort of with attention editing without this optimal control? This is a standard ablation question you could ask. And so here's an example. Let's look at this. I give you this as a reference style and ask you for a piano. If I just give you a piano, then the image you're going to generate is this. So this comes back to the question I think you're asking about what happens when you just run this thing. And then you could just do sort of some naive attention. You could just paste some attention weights together. I don't want to get into exactly what attention engineering is going on. If you do the naive thing, you can get something really bad looking. So you need, the point of this is you need some clever attention engineering and the optimal control combined together to actually get something useful. So both these pieces were actually important in this algorithm.
The idea that you put it through the attention network, you get whatever value and you add it together, something like that.
If you do that, it breaks. Because you see, the problem is there's a normalizing layer so how do you, basically, essentially this is a problem, right? If one set of weights was much larger than the other, they're not in the same scale. And when you push it to the normalizer, then it gets muddled. So you need to do something else. And so that's, I don't want to talk about that, but because
So in the control problem, why do you have that integral of the square norm of?
This is just a standard optimal control problem. I mean, you are asking why did we square norm? It's something for which, honestly, in the closed form setting, we could actually solve this for a toy Gaussian linear problem. This is a classic JB equation. To get some intuition on what the algorithm should look like. And then once you do that, the actual algorithm, we don't solve this optimization problem. We are actually just taking a gradient step in some manner.
So why do you want to keep that particular portion small? Like
why is energy the right thing to minimize here? Yeah. This squared energy, is that your question?
Right, yeah.
You could do anything else as well. We just happen to pick.
So I'm just saying, like, you can just keep the terminal cost.
Good. You could, if you put only a terminal. So actually what you do is the following. If you apply the solution to the HJB, okay, you want only the terminal cost, but if you don't put any trajectory cost at all, the solutions will be really weird. What you do is actually put an energy cost for the thing, put a constant weight for the terminal cost and for this cost, and let this weight go to 0 in a certain manner, the weight for the trajectory cost. And that's what leads to this particular solution you're interested in. Okay. So it is finally only the terminal cost, but done in a certain style, starting from this and pushing it down to 0 in a limit. You can do style synthesis based on this kind of stuff too. So this was actually interesting because previously, if you are doing training-based approaches, and say I give you this image, and say interpolate this and generate a tiger. There is no clear way, because I don't have any data of what that interpolated style would look like. But you can do these kinds of things now with this, because you have two different terminal costs, you just switch between them. Okay. And I think Karthikeyan is doing these kinds of things if he's here in other contexts as well. But this is just an interpolation here. Okay. And you can, by choosing the strength of the interpolation, you can get all sorts of novel styles in this process. I wish I had a good answer. No, I'm talking about practice here. This works. Okay. At this point, all theory is off. That's my honest answer here. Okay. That's why I didn't talk too much even. For the first part, we have theory, but it's in a setting which is so stylized that it's a lean. So far, the encoder is linear. It's a Gaussian. The ground truth is some high-dimensional Gaussian. Then you can say something. But I'm not sure it's sort of very interesting to talk about it, which is why sort of I think what is useful here is that we started with a toy model to get a way of how to build this. The practice of this is, I think, sort of more interesting, which is why I'm focusing on the practice side of it. These are sort of examples of in the wild. So these images are not from ImageNet or any such thing. This is just wild. Somebody drew some person. It's a single image. You can again give a caption. You can see the quality of sort of the output for these kinds of things. So all this was done to sort of make sure that this is what productionizable essentially. Okay, so this is, as I said, they're productionizing in various pipelines, including Pixel, Chromebook, and something else with YouTube. So it has seen quite a bit of attention in the community. And people have built up this in different ways. I want to switch now. I have about 30 minutes. Okay, good. To talk about rectified flow. So did Dheeraj talk about flows, RF? Okay, so let me again then quickly just tell you a little bit about RF, and then we can build off of that. Okay, so even the algorithm I talked about right now, RB modulation, requires an optimization in the image space. It's a lower dimensional thing, but you need to sort of do a gradient there. Can you do something completely gradient free? Can you edit in a gradient-free manner? That's the question. Okay, and that's what RF inversion is. We want to do is the first algorithm for inversion and editing with rectified flows, and it avoids any test time optimization. And because of that, you can put it on an edge device such as a Pixel or a lightweight machine. So these are some examples of the kinds of things we want to do. I give you a reference content, which is this cat, and say silver cat sculpture, and without gradients, I want to edit it to get this image. So this is what I mean by gradient-free editing. It's only stylization. This does not do content style composition. For content, we will need to do some gradients plus this. Just for straight stylization, for sort of sketch to image, things like that. We can do that. It's more limited, but completely gradient-free. Okay. This was in iClear this year. This is with again the Pixel team and the Imagine team. So what is rectified flow? Okay. So in this cartoon, think of this bubble as samples of noise, Gaussian. Okay, let's just think of each point as a sample of Gaussian. In this cartoon, each point here is a sample of an image. You want to construct a vector field VT, which takes xt, which is initially a sample from, say here, noise, and pushes it forward to a sample of an image. It's a coupling, essentially, through this flow model. This flow model evolves as an ODE. In fact, we know that even if you don't go to rectified flows, we know that we can do that even with just a diffusion model by essentially the ODE versus SDE equivalence, right? You write the Fokker-Planck equation, look at the second order term, do the usual log trick, pull it in the diffusion term, and this is a well-known idea from 30 years back. And so you can get a flow model from any diffusion model. And I think you've seen this derivation last week. So we can take any diffusion model can be converted into a vector field. And if you have such a vector field, what you would do is you would just basically sample noise and send it through this, and you'd end up with an image. Okay. RF is a different flow model. And essentially, it leads to a straighter path than diffusion. Okay, that's basically the reason. I will talk about what the RF objective is. And the reason of straighter paths than diffusion is that it leads to fast sampling. In reality, these are discretized and they're piecewise linear. You just do a piecewise linear interpolation. So if you are the straighter the path, the coarser the discretization can be in terms of practice. And you want small number of steps for speed. Okay. So what is inversion? Inversion is essentially the following. Okay. If I have an image, I want to go backwards to the noise. That's what is inversion. This generation problem is start from noise and go to an image. So an inverting algorithm would be of the following type. If you would start with an image, you would run a flow model backwards to get to noise, edit the noise, and then run the flow model forward to get the new image. Okay. What do I mean by run a flow model backwards? This is an ODE, this vector field. So the reverse of this vector field is if this time goes from 0 to 1, it will just be minus V of 1 minus T. That's the flow model. That's the model that goes the other way. So you can take, if you have a function Vt, then you can always run it backwards by just changing the sign on it and correcting for the time. Okay. So that's what I mean by running a model backwards. So this, if you could do this invert, edit, and move forward, then there's no gradient in this process. And so this is very easy to deploy in production. Okay. The question is, how do you get this kind of inversion to work? Question? Okay.
So why are you inverting?
I want to go from here to here. Okay. The pipeline is going to be go from this to go back to the noise, do something to that noise, and then start from the noise and run a field forward. Okay, to get this. This is the sort of inversion pipeline I have in mind. I haven't told you how this is going to happen, but this is the pipeline that we want to build. Okay. And so here are examples of the kinds of things we can do. By the way, these are all real examples from RF inversion. This is editing, but you can do other things as well. You've got images which are not quite images yet. They're close to the manifold of images, presumably, but not really well-defined images. You can go somewhere, you want to edit it, and come back. So this is called stroke to image. Okay, you can undo sort of corruption while editing. So this is what we'd like to do, again in a gradient-free manner. So when we developed this, there was no algorithm to directly invert and edit. Inversion is possible in SDE models of our diffusions, but they sort of lead to inconsistencies due to nonlinear sample paths, and also sort of stochastic models have some issues. I'll talk about that maybe in another 15 minutes from now. Okay. Alternate methods to maintain consistency. I talked about things like RB modulation, much more expensive because they actually require gradients. So if you can do this without gradients, it's worthwhile. Okay, so as I said, you want to simulate an ODE to generate samples. So there's a vector field or a drift. You initialize it with some any distribution. Here it's Gaussian. Run it, and starting from that, you run this thing. You're going to get images. Okay. I'm not going to get into. So this is all I need for what rectified flows are. You've presumably seen much more on how you train such a model and how it's different from diffusions in Dheeraj's tutorial. So RF inversion is the following. I said there's noise and there's images, but let's sort of, at least as a cartoon mental model, break up noise into two parts, typical and atypical. So these are, if it's Gaussian, these are close to the mean, presumably, and these are sort of off from it. Of course, if you have a distribution which is absolute, like a Gaussian, in principle, you can generate any sample is within its domain. but there are some samples which are, I'm being very soft here. This is not a mathematical statement. There are some samples which are much rarer than others. And I want to sort of have this cartoon here. Similarly, in images, there are images that are typical, and there are things which are not quite images. They are atypical. Let's group it in this way. Let's pixel space. How it works in latent will vary. Yes, but that's a detail that is orthogonal to what I'm talking about. So for conceptually, we can just think about pixel space. So you can start from an image, and you run the following vector field. You had learned a vector field VT, which was the generative model. So the reversal is UT is minus V of 1 minus T. That will go this way. Presumably, images will become typical because that's how it was trained. It was trained using, how was RF trained? Using you're coupling every image with a typical noise sample. Okay, so this coupling is there. But if it's something which is atypical, presumably it goes to something atypical. Okay. Now let's bring a control. Let's do the following. Okay. What I'm going to do is come up with a new coupling, which is the following. For every image or close to image, I could just find a path that connects it to a typical noise point. How you do it? Something. So you pick an image. You pick an image which is Z1. You pick a noise which is Y1. Put a terminal constraint. Put any cost you want. Okay. We put a quadratic because we want something very fast. We'll see what it means in a second.
Coupling the atypical data with the
I'm coupling every image with a noise, whether it's typical or atypical. I'm constructing another coupling. Okay. Why? We'll see that in a second. So we are going to do the following. So for any, let's look at this atypical. There are 2 points. Now there are 2 couplings. This one is coupled to an atypical with our controller. This is coupled to typical through the RF. Let's interpolate between these 2. Okay. How will you interpolate between these 2? You want to essentially push this point closer to this to be consistent with this. By actually, while you're moving, you interpolate between these fields. Okay. So graphically, what you would do is for any image, you'd push it into the typical part of it. And what will the inversion do now? Now, starting from that point, you run the inverted coupled field, okay, which will get you back here. So this is essentially RF inversion. We have interpolating between 2 forward and backward vector fields. So that's the mechanics of it. What is happening? I'll give you a more I think a better way to sort of see it in a minute, and maybe then I can answer some questions on this. Okay.
You got the control, you haven't yet explained.
I did. Well, I sort of explained. It is just this optimal control problem, which has a closed form expression. Okay. I want to find a low energy path. Why quadratic? Same reason. It's something for which we know how to solve this in closed form. P1 is Gaussian. Z0, Y0 is here. Yeah. Okay.
So can you again show the control, the optimal control problem? Can you maybe please explain the terms? So
okay, the optimal control problem is the following: find a low energy path, C is some cost, okay, over this thing. That's the path cost. And there's a cost for making sure that when this is pushed forward, you start from this one, you push forward, you get here. That is Z1. It should be close to the Y1 which you are sampled. So the terminal is what is the most important part.
Y1 is sorry.
So what did you do? You picked a Z0, you picked an image, and you picked a noise sample. And you want to push this, you want to couple this image to that noise sample. So that's the coupling term. Okay.
This is the optimal velocity field that leads to minimizing this.
With respect to this cost function.
Okay.
Okay. That is the controller. No, I want to create a new coupling between images and noise, okay? One-to-one coupling. So essentially, I will view this point as a surrogate of that image in this space. And then I can do edit. When I invert from that and interpolate, it basically grounds in the other direction. It essentially pulls it back towards the image you want. And that sentence is not going to be meaningful right now until 3 slides from now.
So you just take a set of images and then you just take a set of points
And
then
create this coupling.
some arbitrary coupling.
Yes, this coupling.
Minimizes this.
Exactly. This is the coupling.
No,
I'll
so
give you a
from
closed form
Z1
expression. I'll give you a closed form expression for this thing in just
No,
a
I'm
second.
saying like Z1 and Y1, like how do you decide the indices? Like Y1 was in this space.
Oh, I pick
Z
pairs.
is-
I pick you give me an image. So let's say in test time, what am I doing? I give an image, I'll pick a noise and say, this is my coupling.
The noise is independent of this. Right?
Yes,
You're
there
just
is.
picking some random
I'm picking a typical, but because I'm picking it, it's most likely a typical noise. So I'm coupling any image or non-image to a typical noise. That's really the point.
Yeah, typical noise, but that need not be the noise which would have generated
Of course
the
not.
image when you.
This has nothing to do with the flux model. So there are two fields. Flux has some coupling. This is some completely independent coupling. Okay, and we'll see what the point of this in a few minutes.
Sir, what is the cost there in that?
Just quadratic. Say put C equal to 1. Okay, identity.
Are you learning anything there?
No.
You're not learning
No,
anything.
there's
It's
no
just
learning
like,
there.
At test time, you can solve.
Correct.
The optimal
Correct. There is no
control.
learning going on there. Okay. So I want you to think about this to this following directed graphical model. Okay. So suppose I gave you this following question. Imagine if this cat were a silver sculpture. Okay. Let's go through sort of a directed graphical model view of the world. Okay. What is a directed graphical view of the world? There are nodes. There are nodes x0 to xn. Okay. These are my variables. There's for each node there are some parents. Okay, and if you look at something called a structural causal model, for each node you can write it as some function of those parents plus some independent noise. So really, the world model is this is the Perlian view of sort of causality. That's where this is coming from. You got this graph. You got exogenous noise at each node, and you got dependencies in this graphical model. Now, if I want to do any sort of editing in reasoning with this kind of a model, what would you do? Well, you would say, I will first abduct to the noise. So if I see a particular state x0 to xn, I give you that sample, you would, in principle, go back to the noise that led to this worldview, this sample. So this is called noise abduction in the Perlian setting. Okay. So you actually you would, in principle, try to find the noise that generated this model. Once you find that noise, hold that noise. You want to change the world, so you will change some conditional distribution. Say this statement will correspond to in maybe one of the particular nodes, change the parents, excise it. It's essentially a do operation in causality language, right? But in a graphical model sense, all you're doing is you're changing the condition for one node and its parents. You're changing the conditional distribution. Then you feed that same noise which you're retrieved to this new model, and this is sort of what you would do to sort of do this kind of counterfactual, which is imagine if this cat were a silver sculpture. So essentially, RF inversion is an implementation of this way of thinking, which is it's the first step of inversion is going back to a noise model which would generate this world. I will do text conditioning. When I'm actually going from here to here, we are actually putting new text inside, which is actually changing the way the world is going to evolve. And then you generate through the reverse flow, which is the prediction. Okay? So this is essentially the RF inversion pipeline. And let's talk about what, if I don't do the controller, what actually happens. So let's start from a reference image here. Okay? Let's do things in continuous time. Suppose I had the vector field at every point in time. I'll run it forward, run it backward. Theoretically, I should get exactly the same image. The problem is you're discretizing and you actually don't have the reverse vector field. how you learn the reverse vector field is the following. At any point, you look at the forward vector field and then flip it around and assume that that's the same thing, and then take a big step. So if you discretize coarsely, you see the reversal and the forward actually diverge from each other. And this is what happens with a reasonable level of discretization.
Vector field. It's a completely different image because of the discretization.
That's all. This is it. If there's no condition, ideally, in theory, if with null text, because if you do fast, if you have finally done this, you should get back the same thing, because there's an ODE, there's no stochastics anywhere. You're just going this forward and backwards, you should get to the same point. This is what discretization error is giving you. What our controller does is essentially a negative feedback. It's coupled, remember the noise, it's coupled to a particular image. So it's always pulling it back that way. When you interpolate between those two, it's pulling it back to sort of features of that image, and that's what is coming, that's what you're getting out of this. And now if you do text editing, you can get this. It's not exactly correct. For example, you do see that this is not identical to this. There is some corruption, but it is pretty close.
So here the controller you're doing to go from the noise to the image.
There are two, I talked about one controller. The analog, there are two controllers. The same controller actually has a forward and a backward. So it is
applied in the
it's applied in both directions. We applied, you don't need to apply it in the forward direction. It's not from image to noise, right? But because you could just, but you can just run it as, it doesn't hurt. You just keep the controller for forward and back. You can just do this. To get to, all you need to do is to get to a noise point and go back.
Using the controller, you can go from any noise point to this exact same image, right?
Correct. It is not, no, wait, the controller is pulling towards one image point. That's the field, right?
Yes.
Yes.
So
it's
it doesn't matter like
this.
what the starting point was, like you would go to
Yes, the controller is pulling towards an image. The rectified flow, like RF flow is pulling towards the manifold of images. And so when you do no null, it'll come back to this image. Okay? But when you start doing text editing, that's where interesting things happen. The interpolation of those fields will get you something. This is just basically an ablation study. Okay? This is not interesting, these two, except to say that you need some controller to sort of help with this discretization issue. But this is what is the interesting part when you're getting something non-trivial out of this package.
How do you control the relative power of the text conditioning versus like the controllers?
There are hyperparameters, we have tuned it. Okay, we have some prescribed weight schedule, which is there in the flux. If you go to Comfy UI, it has some weight schedule. A lot of people have also played with it, and we have a certain what makes sense. We have something. That gamma parameter there. How do you sort of move between these two? That's there. It's not actually like a fixed parameter.
How much weight you give to text conditioning versus how much weight you give to the control.
There are two fields. How much weight you give to our controller, how much weight you give to the text, to the flux controller. You can pull this back together. It's eta 1 minus eta, we just write it this way. And actually it's eta t. You could do a time varying thing. Okay. Yeah. So these are other, so you can, but you see, you can't, the way I've described it, doing content editing is tricky here. This is all about these kinds of text. It's text-based editing is really what this is set up for, the way it's described here. But you can do experiments about multiple times. You can send it back and forth multiple times and see what comes out of it. And this actually works quite well. In the last 10 minutes, I want to talk about a stochastic sampler for rectified flows. So rectified flow is a deterministic, deterministic velocity field. So the reason people like it is it's fast. So why would you ever go try to create something stochastic out of it? The reason is that there are many algorithms people have built which rely on the stochastic nature of the diffusion sampler. So you want to, because the state of the art model today is flux, which is a flow-based model, you want to somehow modify it, or you want to do some wrapper on it so that all the other algorithms people have developed for stochastic samplers can be sort of dropped into this. So a stochastic sampler is useful to the community. The second thing is that stochastic samplers have robustness of corruption in the following sense. Okay? A flow-based model is just an ODE. It takes a point and puts it somewhere else. A stochastic sampler is a Markov chain. It doesn't matter where you start, it will get to the invariant measure. So there's a natural way to pull back towards images and noise will not propagate through. So that property is sometimes useful. Okay, so stochastic samplers are slower, but they are sort of more robust for some applications. So what you can show is the following. If you look at if you write the RF, if you look at the rectified flow and you ask what is explicitly the vector field, we actually computed it and you get this. If you look at it, this is some other affine transformation of the usual score. Okay, there's just a time change that is going on. The standard DDPM type things had some other constant, the time, some CYT minus CYT minus C2 grad log PTYT, right? That's essentially the form of this. It's saying that this is just a different time interpolation that's going on. So, which means that in principle, you can take a standard DDIM controller and make it a flux controller by doing this kind of a reweighting. Okay. Of course, the thing is that you should be able to interpolate at those points in time as well. Okay. The optimal control we talked about, I was being very dismissive of it. It's actually very simple. There's a closed form solution for it, which is exactly this. The control is essentially the following. If you want to pull towards y1 and you're at yt, look at the difference divided by 1 minus t. Okay, as you get close to 1, you're going to make the strength very large, and you're further away, it isn't. It's a trivial solution. It's not very deep here at all. Okay, that's all the optimal controller is here. So this is essentially what you are saying. You're just pulling it towards y1. Okay, that's all you're trying to do. And what we are doing is interpolating between these two, this one and this one. This one is making sure you're pulling it back towards the image which is keeping the features you have. The other is sort of the flux controller. Yes. Well, it's in somewhere between the noise and the image space. At y0, it's the noise space, and as t evolves, it's somewhere between this. And so you can actually write. Okay, so now we know this. You can write the controlled rectified flow ODE. You can write the density evolution by continuity equation. You can write what it is. Then you can take the continuity equation and use a Fokker-Planck to get an SDE out of it. Okay, just go backwards, and so you can get a diffusion model in the sense that there's a drift field and there's a time varying sort of standard deviation term in the diffusion term for the kinds of things we are doing, and people have used this. So let me show you some experiments. To have some nice pictures. Yes. So if you do this, you can see that the quality of the images are comparable. This is the standard flux. If you do a flux SDE with similar prompts, you can get images of comparable quality and comparable looks. Okay. So this model is slower, but you're not going to lose performance. It is actually flux-like model, and so people are using this for other projects. In terms of experiments, you can sort of do prompt-based editing. You can do multiple types of semantic editing, meaning I can give you this, I can add pepperoni, I can add mushroom, I can do multiple things, I can edit incrementally, and then this will require some gradients on top of it. You can now combine RB modulation and RF inversion to do content style composition, and we can also generalize to other flow models, for example, SG 3.5. So these are examples with this other model. Google has its own internal model, so you can recreate all this with their own internal models as well. So that's, yeah. I think I'm pretty much out of time. I have 5 minutes. So these are sort of with the SDE model, you can do these kinds of things. You give, now here are more details. You can give very detailed prompts. And Flux generates very, very high quality. I mean, it adheres to the prompt well, but But what we are doing is with the SDE model, it's very, very similar in terms of quality of the image generation. So that's basically what I had to talk about today. This has been, after this, there are a bunch of people who have taken our thing and done video editing. If you look at some of these links, you'll see that you can do RF inversion for video. You can take a base video, you can run this algorithm to add a hat and generate a video, or you can change them to cartoon and so on, like 3 seconds, 5-second video clips. There's a community which has, this actually Flux, this RF inversion actually is part of diffusers now. So Hugging Face has sort of implemented it within their their platform. So yeah, that's basically it. Thank you very much.
Like you want a hat on top or something. Do you ever get junk as well, or is it always a nice picture that comes out? Is there
It's not. There's a lot of parameter tuning on those gammas, which are brushed onto the carpet. But once you get the parameters right, it's much easier to do the tuning on this than other thing because there are just very few parameters. Okay,
Right.
there's not that much. So it's pretty, I think, much easier than other methods. And sort of, which is why really there's a community that has sort of, not a research community, just outside, many developers and others who have taken this on and taken it elsewhere. So for example, somebody, not us, have implemented on Comfy UI. So you can now do drag and drop with this thing. You can visually, you can sort of put this into pipelines and sort of run stuff. Again, this is because I think the parameterization is very light, and so it's much easier to work with this model.
And is there like a good mathematical way to see why this is happening? Why you don't mess up?
Maybe that's sort of what our SDE thing was, to see what is going on, but to say what is the right hyperparameters and to prove anything beyond linear models is, I think, very hard. But maybe, to be honest, this world is moving so quickly here that to sit back and think about the math is, at least we haven't had the time to do this. This was just like a few months old, this thing. And already there's something else is moving ahead. So it's a non-answer, I know, to your question. But the answer is I don't have a mathematical model to say what the right thing should be. It's an interesting question. But yeah.
Because what you're doing is kind of a commonsensical shift, right? And control theory is justified.
Control theory, yeah, the control was telling us that you need to have the right negative. In retrospect, it's commonsensical to do this. But when we started, we said, let's build the optimal control frame. It started that way, and that's why it's grounded in this control language. And then we realized that's all is going on, which does this thing in retrospect. But and in some sense, that's why it's powerful, because a very simple algorithm to actually implement. And so you can implement at scale, and it really, because of this, it really scales up.
Right.
Okay, thank you very much.
I guess we have a tea break now. We'll resume at 3:45 with Subro's tutorial. 3:45, yeah.